Hello friends, I welcome you in lecture number 2 on residue integration of real integrals. In previous lecture, we have discussed the method of evaluating improper integrals using residue theorem. So today we are going to discuss one example on evaluation of improper integrals using residue theorem. So before going for this example, we just recall the steps of the method. So we have discussed that we can evaluate certain types of improper integrals using residue theorem. So which type of integrals can be evaluated? So here our function fx is a rational function, say division of two polynomials, where this denominator qx is non-zero for every x on real axis, that is q has no zeros on real axis, and degree of q is at least 2 higher than the degree of p, that is degree of q is strictly greater than degree of p plus 1. So if these two conditions are satisfied, this improper integral is convergent and we can evaluate its value using Cauchy's residue theorem. So for that we consider complex analog of this function, that is we replace x by z and we write the corresponding complex function, and then we find out isolated singularities of this function f of z which are in upper half plane. So this function is not analytic at all those points at which this denominator becomes 0. So we will find out zeros of qz, or we will solve this equation to find out poles of this function f of z. So suppose poles are z1, z2, zn, and suppose all these poles are in upper half plane. So the poles which are not in upper half plane, we will not consider those poles. So once we find out poles of f of z, then we will calculate residue of f of z at each of these poles which are in upper half plane, and then as we have discussed in previous lecture, that value of this improper integral is nothing but 2 pi I times sum of residues of f of z at all these poles. Sum of residues of f of z at poles of f of z in upper half plane. So this is very easy. We just have to check these two conditions first, whether qx is non-zero for all x belongs to R and degree of q is greater than 1 plus degree of p. If these two conditions are satisfied, we can apply residues theorem. So after that we will consider corresponding complex function which is also a rational function. Then we will find out the points z at which qz becomes 0, and those points will be poles of f of z. So whatever zeros of qz we obtain, we will check which values among these z1, z2, zn are in upper half plane. We are interested in the poles of f of z in upper half plane only, and after finding out poles of f of z in upper half plane, we will calculate residue of f of z at all those poles in the upper half plane, and then we will remember this formula. This improper integral is equal to 2 pi I times sum of residues of f of z. So with this in mind, let's try to solve given example. Okay, so we are asked to find out this improper integral from 0 to infinity dx over x square plus 1 whole square. So first we know that this function here f of x is 1 over x square plus 1 whole square, and it is clear that here if we replace x by minus x, we will have fx for all x. Okay, so this function is even function. So therefore fx is even function, and we know that if this integral is convergent and fx is even function, then this is equal to 2 times 0 to infinity fx dx. So therefore integral of fx in the range 0 to infinity will be equal to 1/2 times integral of fx from minus infinity to infinity. So we are asked to find out this integral, but we have formula for this integral minus infinity to infinity fx dx. So first we will calculate value of this integral, and this integral will be equal to 1/2 of this value. So now first we check whether fx satisfies that conditions or not. So we can see fx is a rational function with numerator is constant polynomial and qx equal to x square plus 1 whole square. So if we simplify this q, then degree of q will be equal to 4 and degree of p is 0 because p is a constant polynomial. So we can see degree of q equal to 4, which is greater than 1 plus degree of p. So degree of q is at least 2 higher than the degree of p. So that condition is satisfied, and here qx is x square plus 1. So it is clear that qx is non-zero for all x belongs to R. So those two conditions are satisfied, that qx has no zeros on real axis and degree of q is greater than 1 plus degree of p. So therefore this improper integral is convergent, and we can use Cauchy's residue theorem to find out value of this improper integral. So we first consider complex analog of given function. Given function is fx equal to 1 over x square plus 1 square. So in that function, here we replace x by z and we will get the corresponding complex function. So let f of z is 1 over, it is x square plus 1 whole square. So here we have 1 over z square plus 1 whole square. Then we find out poles of f of z. So here we can see f of z is rational function, so it is analytic everywhere except at those points for which denominator becomes 0. So first we try to solve this, for which values of z denominator becomes 0. So this is 0 if z square plus 1 is 0, and this is z square equal to -1, which we can replace by I square. So this is z equal to plus or minus I, that is I and minus I. So f of z is analytic everywhere except at these 2 points, z equal to I and z equal to minus I. But we can see z equal to minus I is in lower half plane. Okay, here we have, suppose this is rough sketch. So here x axis, y axis. So only z equal to I is of our interest because it is in upper half plane, and z equal to minus I is in lower half plane. So we will not consider z equal to minus I. And if we recall, we have to consider a simple closed contour which encloses poles in the upper half plane. So we can choose radius r large enough such that this z equal to I is enclosed in this simple closed contour, okay, which we have written as union of line segment from minus r to r with this semicircle CR. So this is just for understanding. We need not sketch this for doing this problem, but this is just for understanding. Otherwise we have to calculate poles of f of z, and among those poles we have to find out which pole is in upper half plane. So here z equal to I is in upper half plane, so we will calculate residue of f of z at z equal to I. Okay, this is just for understanding. Now to calculate residue of f of z at z equal to I, before that we write down that clearly f of z has poles at z equal to I and z equal to minus I, among which z equal to I is in upper half plane or above x-axis. Okay, so we are interested in z equal to I only. So now we calculate residue of f of z at z equal to I. Before that we rewrite our function f of z. Our function is f of z equal to 1 over z square plus 1 whole square, and we can rewrite z square plus 1 as z square minus I square, because I square is minus 1 and square here. So this is now, this is I square is minus 1 minus 1 minus 1 plus 1, and z square minus I square is z plus I times z minus I whole square. So we will have square of z plus I times square of z minus I. Now we are interested in the residue at z equal to I. So what we will do is we keep this quantity z minus I whole square in the denominator, and here we consider 1 over z plus I whole square. So if you are not familiar with residues, you can watch my lectures on residues. So this is equal to phi of z over z minus I whole square, where phi of z is 1 over z plus I whole square. Now this function is analytic everywhere except z equal to minus I, at which denominator becomes 0. So this is analytic at z equal to I, okay, because we have here I. So phi of z is analytic at z equal to I, and value of phi at z equal to I will be equal to 1 over I plus I whole square, that is 1 over 2I whole square, which is equal to 1 over 4 into I square, which is minus 1 by 4, and we are interested that whether it is non-zero or not. So phi of z is analytic at z equal to I, and value of phi at z equal to I is non-zero, and f of z is written as phi of z over square of z minus I. So because we are having square here, we can say that f of z has a pole of order 2 at z equal to I. So therefore f of z has a pole of order 2, or we can say that double pole. Pole of order 2 is known as double pole. Pole of order 1 is known as simple pole. Has a pole of order 2 at z equal to I, and we are interested in the residue. So residue of f of z at z equal to I will be equal to value of first derivative at z equal to I divided by 1 factorial, that is phi dash at z equal to I. Now we find out first derivative of this function phi of z, and then we calculate its value at z equal to I. So now phi of z is 1 over z square plus 1 whole square, 1 over z plus I whole square. So this I can rewrite as z plus I to the power minus 2. It is 1 over z plus I whole square. So we can rewrite this as z plus I raised to minus 2. So if we differentiate with respect to z, we have minus 2 times z plus I to the power minus 2 minus 1, which is minus 3, into derivative of z plus I, which is 1. So therefore phi dash z is negative of 2 over z plus I to the power 3. Now we are interested in the value of phi dash at z equal to I. So we put z equal to I here, and we have I plus I to the power 3. So this is now minus 2 over cube of 2I. So therefore phi dash I will be equal to minus 2 over 8I cube. So now this is minus 1 by 4. I cube can be written as I square into I. So therefore phi dash at I equal to, now if we put I square equal to minus 1, we will have positive sign. So we have 1 over 4I. I square is minus 1, so negative, negative, positive. And we know that 1 over I is minus I. So we can write 1 over I equal to minus I, and we have phi dash at I equal to minus I by 4. So now we substitute this value here, and we obtain residue of f of z. So residue of f of z is equal to phi dash I, and phi dash I is minus I by 4. So therefore residue of f of z at z equal to I will be equal to minus I divided by 4. And there is only one pole in the upper half plane. So now we can apply that result. We know that integral from minus infinity to infinity fx dx will be equal to 2 pi I times sigma residue of f of z, or we can write that sigma residues of f of z simply, or sum of residues of f of z. But here there is only one pole, so we have only one value, minus I by 4, so that we can write here minus I divided by 4. So this 2 will cancel out, and here we have minus pi I square divided by 2. Now if we take I square equal to minus 1, negative, negative, positive, and we have pi by 2. So therefore we obtain that value of this improper integral by residue theorem is pi by 2. And we are asked to find out this value, integral from 0 to infinity fx dx. So this is equal to 1/2 times minus infinity to infinity fx dx, because fx is even function and this integral is convergent. So it is 1/2 times pi by 2, that is pi by 4. So therefore integral from 0 to infinity, now we can put value of fx, which is x square plus 1 whole square, is pi divided by 4. So it is very easy to evaluate certain types of improper integrals using Cauchy's residue theorem. So let's summarize all these steps. First we consider this given function as fx, then we check whether those two conditions are satisfied or not. So we consider px equal to 1, qx equal to x square plus 1 whole square. So it is clear that qx is non-zero for all x and degree of q is 4, which is strictly greater than degree of p plus 1. So because these two conditions are satisfied, we can apply Cauchy's residue theorem, and this improper integral is convergent. Now here range of integral is 0 to infinity. So we have used the fact that fx is even function, therefore this integral from minus infinity to infinity is 2 times integral from 0 to infinity. So therefore this will be equal to 1/2 times value of this improper integral. So we are evaluating this improper integral. So for that we consider complex analog of this function. So here we replace x by z. So we obtain f of z equal to 1 over z square plus 1 whole square. Then we find out poles of f of z. So poles of f of z are nothing but the values of z at which denominator becomes 0, because f of z is a rational function. So its poles are values of z at which this polynomial in the denominator is 0. So we obtain that denominator becomes 0 at z equal to I and z equal to minus I. So f of z has poles at z equal to I and minus I, but we are interested in the poles in the upper half plane only. So z equal to minus I is in lower half plane, so we will not consider z equal to minus I. We will consider z equal to I only, and then we calculate residue of f of z at z equal to I. For that we express f of z in this form, phi of z over z minus I whole square, and where phi of z is analytic at z equal to I and value of phi at z equal to I is non-zero, and because this power is 2, f of z has a pole of order 2 at z equal to I, and residue of f of z at z equal to I is phi dash I over 1 factorial, that is phi dash I. Then we calculate first derivative of phi, and using this we consider phi dash I, and we remember this formula that if conditions are satisfied, minus infinity to infinity fx dx will be equal to, okay, we will always remember this formula, that if fx satisfies those two conditions, that qx is non-zero and degree of q is greater than 1 plus degree of p, then this improper integral is convergent and it is equal to 2 pi I times sum of residues of f of z in the upper half plane. Okay, so then we substitute residue of f of z, which is minus I by 4, and we obtain that value of improper integral is pi by 2, and therefore this value will be equal to 1/2 times pi by 2, which is pi by 4. Okay, so in this way we can evaluate certain types of improper integrals using Cauchy's residue theorem. So I hope you understand this example. Thank you very much.